Problem 10.31 show that if theta square is a biased estimator of the theta, then the expectation of this squared thing here is equal to the variance of, so this is called mean squared error, right? That's what we learned in class. And it's equal to variance of theta square and plus the square of the bias. This is actually what we showed in class, also on the slides. So I'm going to show that one more time here. So let's denote the mu to be the expectation of the theta hat. Remember that the theta hat is a statistic, it's a point estimator, so it's basically, it must be a random variable. So the expectation of the random variable becomes some constant mu. Okay, so we can just denote it by this constant by mu. So the expectation of the square of these two things, which is the MSE of the theta hat, mean squared error of the theta hat. So this is equal to this. So what I did here is just to subtract the mu and add it back. So it didn't change anything. Now I have the square. Sorry, I should have the square inside. So it's actually this plus this squared. So I can break the square. There will be this squared, which is what I put here, and then 2 times this times this. So that's what I have here. Because outside there was the expectation, so I need to apply the expectation in there. But remember, this is just a constant, so I can pull it out of the expectation. And also, lastly, we have the square of this thing, and then take expectation. But because this is a constant, so the square is still constant. You take expectation, it's just that square itself. So it's just this. Okay, so now this thing here, or just copy it down here. For this middle term here, this expectation of theta hat minus mu is just 0 because the expectation of theta hat is just mu itself. So if you pass this expectation to this guy minus the expectation of the mu, which is just mu itself, we'll say that both the two terms cancel. So that's why this term is 0. So that makes the whole middle term become 0. And then we'll have this term left, which is here. Now, by definition of the variance, this theta hat minus its own expectation, square it, and then take expectation. This is by definition the variance of theta square. And this is the bias of the theta, because this thing here is just the expectation of the theta hat. So this is just a bias, and we just square the bias. That's this. So that's how we proved this identity.